Hello everyone, welcome to chapter 3. So this chapter has a really fun title, doesn't it? It says functions as infinite dimensional vectors. So we're dealing with infinity. Yes, so what do we want to think about? What's actually happening here? We kind of need to reintroduce ourselves to vector spaces. I know this is something you probably talked about in linear algebra, but we're going to reintroduce ourselves to vector spaces and find out that in fact functions themselves, like a lot of the functions we interact with on a day-to-day basis, are themselves elements of vector spaces. But it turns out that the dimension of these vector spaces is infinite. So we have to make this formal, right? We have to understand what does it mean to truly be an infinite dimensional vector. But to do that, let's start with vector spaces. So here I've presented the definition of a vector space. And primarily, the vector space is a pairing of a set. I'm going to call a set capital V, but it's the pairing of a set capital V along with a field and this idea of addition. And of course, the field adopts addition and multiplication along with it, but the vector, the set V, only has this very special definition of plus on it. And the following, these are called axioms. We call these axioms not to be confused with axioms in logic, where in logic those are the axioms that we just assume to be true before we develop all of our logical systems. The axioms here are like the word that we use, axiom, refers to just like a collection of criterion that exists within a definition. So these are called the axioms of a vector space. So anytime you see a definition which defines a mathematical object and it has to satisfy like some numbered criteria, those criteria are called the axioms of that definition. So anyway, that's what we have here is we have these four axioms that get satisfied by a vector space. And my addition operation, which has been defined for two elements in the vector space, has to actually be commutative. Okay, so that means it behaves like our standard addition. Makes a lot of sense. We need an element that we call the zero of the set, which will be the vector space. And that element needs to have the property that it's the additive identity with the addition that we've defined earlier. And then we need some special properties from the field, right? So if we have an element in the field that we're including in our vector space, we can well define like the action of the element A on the element of the set V, and that just keeps me in this set, right? So really for every A in the field, we consider some map. Maybe I'll write this down, it'll be more explicit. For each A in the field, we have A as a map from V to V. Okay, so in some sense we assign a map. So the A in the field gets assigned this map, which maps an element of V to another element of V, and then that specific map for each A in the field has to satisfy the natural properties that it should assume from the field itself. So for example, if I take two elements in F and I add them together against an element in V, right, the addition of the two maps, if I compute them separately on the V's and then add those two elements of the set together, then I get the right elements in the set. And then similarly, I have like a distribution law. So if I define my map on the sets here, if I add two elements of the set, I can actually distribute that in the way. And then say with multiplication, I actually have associativity with multiplication on these elements of the set. Okay, so I know this is really like a very abstract definition, but it's the most general one we have for vector spaces. And primarily in this class, we want to be thinking of the same stuff that we've always thought, where the vector space V, this is the bold vector space, is basically the complex numbers to the nth power. There's not too many more general ideas we have to think about vector spaces, except for the final case where we get to at the end of the chapter, which will kind of be like the complex numbers to the infinite power. So primarily, yes, we can be very, very abstract when it comes to vector spaces. And in fact, your very first exercise deals with these. The first three exercises deals with a slightly more abstract version of these, just so we feel a little bit comfortable. But primarily just think in our heads, especially when we're dealing with these n-dimensional C numbers or the infinite dimensional C numbers, which these are sequences, right? So any countable sequence can be thought of like the infinite dimensional C number. All right. So let's move on from there. There are some extra properties that it technically needs to satisfy, but these are gained from F being a field. So that's nice to know. And then I've presented us with our classic example of R2. And let's just verify that R2 does satisfy the 4 axioms. So the first one says for any 2 elements in the space, if I add them together, I end up with those elements, and addition is commutative. And that's very much true. There is a 0. The 0 vector is the 0 in this case. For all a's in my scalar field, which in this case the scalar field is the real numbers, I can just perform scalar multiplication on the vector, and that's an element of R2. And finally, we have to take care of the 3 special cases of the scalar field. And that's that if I add elements of the scalar field, it's the same. It distributes both inside and outside on the scalar field. And then this is I can also distribute elements of the scalar field themselves, right, onto addition of vectors. And then finally, if I multiply 2 elements of the scalar field, I gain associativity of scalar multiplication. Okay, so this remark is kind of what I was saying earlier about the map that gets defined. It's not, this example is very straightforward why it should, a vector field should satisfy the 4 axioms. But when we get to more abstract cases, which thankfully we don't really in this class, but, be prepared for some courses to give you very abstract situations of vector fields, it's not going to necessarily be trivial that these items 1 through 4 are actually satisfied, because the map which defines multiplication onto the set from the scalar field can be some somewhat arbitrary map that just needs to satisfy some properties. So that's why it's just good to keep in mind that this isn't as trivial as it looks necessarily. Okay, but once we have a vector space, we have a notion of linear independence. And I know we've already kind of been using this in the linear algebra section, but I'm just trying to make things a little bit more abstract here. You've noticed that my summation is summing over n, and I didn't index that from n equals 1 to 10, or n equals 1 to 300, or n equals 1 to even infinity, n equals minus 11 to 24, or something like that. This sum can just occur over whatever I've indexed my vector field by, right? So however many dimensions my vector field is, and we'll see how to define dimensions later. So a collection of vectors in the vector field is called linearly independent if the only collection which solves the equation an vn, right, these are elements of my scalar field, v is elements of my vector field, the only sum of an vn which add up to 0 is the trivial an, right? So that's what I'm saying here, that an has to always be 0. So it's the trivial an that adds up to 0. That's what forces linearly independent vectors here. So I've got an example of these. We can see that if I grab these vectors in R3, that they will be linearly independent, because no matter what I do, adding them, subtracting them, multiplying them by a scalar, and adding them together, the only way I can recover 0 out of these 3 vectors is if a1 is 0, a2 is 0, and a3 is 0. And we can actually see that explicitly by computing row reduction on the matrix, right? If we wanted to solve this problem, we would reduce this matrix to that it is actually row reducible, and of course the right-hand side already being zeros means that, yeah, it's going to be zeros. Okay, now we notice if I just change one element in these vectors, so let's see what the difference is. I've modified a -1 in the first case to a -2 in the second case, and just by changing one element of a vector by one amount, all of a sudden I gain linear dependence, because this equation at the bottom, a1 v1, a2 v2, and a3 v3, does in fact add to 0 for the specific case of a1. So this one is satisfied for a1 equals 1, a2 equals 2, and a3 equals, this is supposed to be a -1 there. That's a little typo. So we can verify this, right? Because if I multiply v1 by 1, then the first term is 1 plus 2 times 0 plus -1 times 1 gives me 0 in the first row. And then if I go to the second row, 0 times plus 2 times -1 is -2, plus -2 times -1 is -2 plus 2 is 0. And then in the third case, 2 minus 2 plus 0. And all of a sudden I end up with 0 in every case. So the definition of a basis is a subset of the vector space for which we have a unique collection of scalars which add up to every single other vector in the space, right? So if I grab a subset of my vector space, I can always find, notably there exists, right? So I can always find a collection of scalars. And more importantly, that collection is unique of scalars for which if I sum these together, I end up with any vector of the vector space. And I know you've all seen this before when it comes to linear algebra. Now here's a remark. We do have non-uniqueness of a basis. It's because you could always take the original basis set, take the union of that set with two of them added together, and then subtract one of the two that you've added together, and you'll still recover a basis. It just won't necessarily be the same basis that you had before, right? So this proposition here that basically says, if I have a collection of linearly independent sets and there exists a set of scalars for which I can find every v, right? So basically that's saying that the linearly independent set is a spanning set. Then I actually have a basis. So I'm going to write this a little more explicitly. All linearly independent spanning sets are bases. So a linearly independent spanning set and a basis are the same thing. That's what this proposition is saying. So this is a classic example of a basis in R3. That's because it's three vectors, and we saw above that these three vectors were in fact linearly independent. So a collection of three linearly independent vectors in R3 forms a basis. Okay, now this next proposition is a somewhat important one. That's that the cardinality of a basis set is unique. Okay, so a set which is maximally linearly independent is a basis. And then more importantly, a minimal linearly independent set which is spanning is also a basis. So it's maximally linearly independent in the space, and it's also minimally linearly independent so long as it's spanning. And that means that the direct corollary of this right there, I say, therefore the cardinality of the subset is unique, right? Because that means if I take one element away, I'm no longer spanning. And if I add one extra element, then I'm no longer linearly independent. Maybe I'll write that down a little more explicitly here. This is saying if I add anything to a basis set, it's no longer linearly independent. But if I take anything away, it's no longer spanning. And that means that its size is unique. That means I can't add any extra elements. I can't subtract any elements. So its size is unique. Now this brings up the definition then, right? The definition of a dimension, the dimension of a vector space is exactly the cardinality of the basis. So once I've found a basis, I take the cardinality of that set, and there's my dimension. What that means, though, the direct corollary of that is I have three choices for a dimension of a vector space is that I have any natural number, I can be countably infinite, or I can be uncountably infinite, because that's what cardinalities of sets exist, right? We have the countably infinite sets, we have the uncountably infinite sets. Now, of course, uncountably infinite sets can be broken themselves into a huge hierarchy of alepphs, but primarily in this course, we're going to be focused on, I say this chapter, in this course, we're focused right here, the countably infinite vector spaces. Okay, well here we can compute the dimension of R3, no surprise there, it's 3. And then we're going to move on to the Taylor series, right? So I just said we're concerned with these countably infinite vector spaces. You might ask, hey Evan, what's an example of a countably infinite dimension vector space? It's the Taylor series. So if we grab analytic functions, right? Recall what I mean by analytic functions. Analytic functions are the functions which are representable by a Taylor series at a point. If I define the basis elements, now I'm going to use, this is something to keep in mind, I will use a boldface E sub n as basis elements. Okay, there's a reason for that. The E is commonly used to denote basis elements because of the Fourier series, which we will get to in a little bit. But I will use En as basis elements for all of my vector spaces. And because of that, if we look here, I'm going to make the definition that E sub n, the basis element, is defined as the Taylor series, I guess, polynomial of nth degree, monomial of nth degree. Okay, So my basis elements are the monomials of nth degree centered at z0. And then if I jump up to my function, I see that every function is uniquely representable against this basis by its Taylor series coefficients. And those coefficients I'm going to call a sub n. Okay, so the Taylor series coefficients exist and they are unique. And therefore I have a vector space, but how many basis elements do I have? I have infinitely many. So there are countably infinitely many of these. Thus, this is a infinite dimensional vector space. Now I haven't proven that the vector space axioms are met yet, but I will in just a little bit. But this is the idea that this is why it's a countably infinite dimensional vector space. So let's scroll down just a little bit. I have a lemma here that proves every single one of these basis elements are in fact linearly independent of the rest of them. And we can prove that relatively easily by trying to form one basis element out of coefficients of the other basis elements, right? If I just moved this term to the left-hand side, that would say that there's a non-trivial linear combination of basis elements that's equal to 0. So this is equivalent to showing linear independence of the left-hand side and the right-hand side if I can force all of the a sub n's to be 0 or I get a contradiction, right? So I'm just going to assume that this is true. And then I see that if I take m derivatives of my monomial, I end up with m factorial. Meanwhile, if I take m derivatives of the right-hand side, I end up with this, which is a little bit interesting of a sum. I'm basically saying, okay, the only terms that survived were the ones that were greater than m. If I take those derivatives and evaluate at z0, then I get 0. So the left-hand side is non-zero, the right-hand side is 0, and all of a sudden I have a contradiction. So therefore, they are not linearly dependent, which makes them linearly independent. Okay, so now I have my vector space of analytic functions. So I'm showing that my vector space axioms are in fact satisfied. Here's number 1. If I take f and g in my space of analytic functions, I can add them together and I still have an element of the analytic functions. 0 is definitely in the space of analytic functions. For all scalars in C, I can multiply an analytic function and still have one. And moreover, if I take two elements of C and add them together, then it distributes properly and distributes in the other direction properly. And also, I have associativity when it comes to scalar multiplication. That's all I needed for a vector space. Moreover, since it's a linearly independent set for which every function can be representable by it, I do have a basis of monomials. Here's a cute little symbol that probably about half of you have seen. This is called aleph null. That's one way that we can represent the cardinality of countably infinite sets. So this is a countable basis, so this is a countably infinite dimensional vector space. Okay, so here's a remark. So just as in R3, we give the basis elements, the representation 1, 0, 0, 0, 1, 0, and 0, 0, 1 is kind of the canonical basis in R3. I can do a similar thing with the analytic functions. So I can actually represent analytic functions. Right, this is f of z. I can represent this as an infinite vector. Okay, now it's a little bit strange. I can never write down every single entry of an infinite vector. I would be writing for infinity. But as long as I have some sort of expression for the coefficients of that specific vector, then I can kind of write it down, right? Like this a sub n has some explicit meaning. In the case of these functions, the a sub n has the meaning, right? I can replace this with f of n, n derivatives of f at z naught divided by n factorial. Okay, so there is truly a vector which can be constructed from my function f, and that vector is infinitely long. I can alternatively think about this just as a sequence, right? So all I'm saying is that this vector contains the same amount of information that the function written as the sum against basis elements does. I can either represent my function as an infinite vector or as a sum against basis elements. So a good example of that, a vector space representation of the exponential function. I can either think of the exponential function as an infinite sum, as its Taylor series centered at 0, or I can just decide, okay, I'm going to represent E as the nice infinite vector 1, 1, 1/2, 1/6, 1/24, and so on, all the way up through 1 over n factorial, and then all the way onwards, right? So this is a perfectly well-defined vector, so long as I'm clear about how I'm defining every entry, and it contains the exact information that e to the z has as a Taylor series. And what's nice about these vector representations is that these allow me to think of and I'm going to put it in quotes, linear algebra in infinite dimensions. Okay, that's the reason why we're introducing these infinite vectors, is that conceptually we can use our same intuition from linear algebra, but now we're going to use that intuition for infinite dimensional objects, like functions. Okay, so now this next remark is a little bit important, because we're very used to having the dot product in something like R3. The dot product is perfectly well defined in R3. If I take two vectors in R3, I dot product them, or I use my new notation of the inner product, and all I do is sum the entries, right? But I can't actually do that. There's no inner product of the vector space of analytic functions, okay? So this representation only gets me so far in its similarities to linear algebra. I can no longer think about inner products of these, and we have a nice little example here. So here I say, just because one can symbolically write, the dot product of two of these elements, doesn't mean that we apply a meaning to the symbols. So if I scroll down, I look at two analytic functions, both analytic at 0, both 1 over 1 minus z, and z over 1 minus z are analytic at z naught equals 0. And so because of that, I have a vector representation of both of these functions. Okay, the first case, it's the vector of all ones. The second case, it's the vector which only has a 0 in the first entry, and the rest of the vectors are all ones. But what I don't have is any notion of an inner product of these vectors. If I decided to try to take the inner product of these two vectors, what I would end up getting is an infinite sum. All right, if I take these and I put a dot product between them and I start calculating, I have an infinite amount of ones, which would just be 0 plus n equals 1 to infinity of 1, which is infinity. So this doesn't make any sort of at least finite sense, and we would have to make some very special definitions in math to account for inner products such as these. And in general, I don't know of anywhere we can do that right now, but there's probably some way around it. There always is. But by and large, we don't want to put an inner product on these because it's not well defined. Okay, but we will see by the end of the chapter that there are some vector spaces with infinite dimension which do admit inner products. So that's something that we want to look forward to, is that some of these will have inner products. We just have to be careful on how we construct our function spaces. Anyway, that's all I have. I hope you enjoyed. Thanks.